So at this very conference last year, I was talking to one of our codec engineers, and we were talking about quality, video quality, not quality of life, because that's what nerds at conferences do. And he said something very curious to me. He said, we can consistently see perceptual improvements in our video quality that were not reflected in our VMAF scores. And that's with some of our new fancy algorithms that he'd been working on. Now, I thought that was very curious because VMAF's actually a pretty good metric. So I sat down to prove him wrong because I'm a big objective quality believer. And I did show him that improvement in VMAF, just not precisely in the score. And that got me thinking. The VMAF score had misled him here. I wondered, being an engineer, what other ways could I make the VMAF lie to me? Could I exploit all of these objective quality video metrics? Hence the talk title, Objectionable Uses of Objective Video Quality Metrics. But also, after writing this talk, I thought it could be titled something like, How Not to Tune a Video Encoder. But more on that towards the end of the talk. First, a little agenda. We're going to spend a little bit of time, for those of you who are not aware of objective video quality metrics, giving a brief overview of those. If you are super familiar with this, check your email for 2 or 3 minutes. Then we'll get to the main course. The main course is going to be how do we exploit those metrics. We'll look at how we accidentally broke VMAF, and then a general assault on video metrics that we compute today, why I think you should still use them, and a little bit of touching on tooling. So what is an objective video quality metric? Well, one, it's objective in that the algorithm computes the score or ranking. It's not something done by humans. Video quality metrics which take human input are called subjective video quality metrics, and those aren't my focus today. Second, we do have a special class of objective video quality metrics called reference-based metrics. Those use the source in their comparison. All of the things I'm talking about today apply to all objective video quality metrics, but I am solely focusing on the reference-based ones, which are the most popular. So, in my experience, there are 3 major ones that people talk about today. Those are PSNR, SSIM, and VMAF. Note, I didn't say best or worst. I will leave that to your judgment and the judgment of others. These are just the ones I see when I talk to my customers out there. First up, we have PSNR. PSNR is probably the oldest and most broadly used metric. PSNR stands for peak signal to noise ratio. PSNR is based on the signal to noise ratio, which is the same thing your Wi-Fi chip measures to talk to your router and give you the little bars at the top. The formula looks like this, which may seem complicated if you're not familiar with it, but it's actually pretty simple. The peak signal here is just the maximum value a pixel can take, called max of I on the right. I is the original undistorted, aka uncompressed source. The noise ratio is that value squared divided by the mean squared error. The max is squared so that they're in the same domain. And then we take the log of the whole thing and place it on a decibel scale, aka logarithmic scale. And mean squared error for us in this case is just the difference between the original value of the pixel and the distorted value of the pixel, squared for a bunch of statistics reasons that I won't get into, and then the mean of all of the squared errors of the pixels in the picture. So if we think about that for a moment, PSNR tells us something kind of intuitive. It tells us how much information made it through in a pure digital sense. Indeed, mean squared error, the basis for PSNR, is something we use to train things like machine learning models. But it's only an okay measure of video quality. PSNR deals very poorly with blurring and a host of other visual artifacts. In particular, the human visual system is heavily driven by shape. It's possibly topological in nature. You can see that in these two pictures, which actually have the same PSNR, but one is visually far worse. The one on the left is effectively one of the results of running tuned PSNR on your encoder, by the way. So we need another metric that captures the shape of an image, and that's why SSIM was added. That stands for the Structural Similarity Index. I won't dive into the math here because it's a lot more complicated, but SSIM captures that shape piece very well. It's not great at capturing texture or color fades. And there's a lot of metrics out there like this. They all have weaknesses. Pictured above is several common metrics, much more sophisticated than PSNR and SSIM. And in every one of these photos, those metrics compute either a high score when they shouldn't or a low score when they shouldn't. So we know even sophisticated metrics like VIF have issues today. So you might be thinking, why not combine these to offset their weaknesses? And that's what our friends at USC and Netflix did. That's VMath, or Video Multi-Method Assessment Fusion. The multi-method is a combination of what VMath calls elementary metrics, like PSNR and SSIM, though those aren't actually used. They are combined using support vector machines, what pop tech loves to call AI today. VMath incorporates an elementary metric to measure more than just the quality of a single frame, and is also thus a true video metric. And that worked pretty well. It correlates more tightly with subjective, that's human-based if you've forgotten metrics, for scoring videos. So how do I break VMath? For PSNR, I can blur the image. For SSIM, I can muck with those textures and gradients. But VMath tries really hard to prevent that. Let's go back to the story I told you. I ran the VMath scores on some videos. And sure enough, the VMath was the same between both algorithms. But watching them, it was pretty clear one was better than the other. And that was consistent across videos, across content, and across runs. And that is something we had confirmed independently by some very, very reputable sources. Now, I looked into how VMath was computed. And one thing that stood out is that VMath uses a simple arithmetic mean to express the average quality of all the frames in a video or sequence. So I plotted Violin Graphs on our RD charts. For those of you who are not familiar with the Violin Graph, that's just a distribution flipped on its side and mirrored so that you can see, for this average point, what actually makes up the underlying average. And when I added our new 2-pass for these videos, something interesting showed up. Do you see it? And if I added our 3-pass, it became very clear what was happening on these sequences. We had the same average, but a far better distribution of frames. Those glut of frames with very high quality were lower, and so were the glut of frames with very low quality. It's actually pretty intuitive that people prefer a video sequence where there are more frames at the average than a split between high and low. Imagine for a moment a scene where every other frame is heavily macro blocked rather than a consistent low level of macro blocking. People will always pick that second one. Now, the VQ experts in the room are about ready to scream, yes, we know this is an issue. It's even in the VMath source. Use a different mean function. Use harmonic or geometric or whatever. But like I said, this is just what inspired me to try to break metrics. So let's craft a theoretical attack on all mean functions. In fact, let's attack generally all of the objective video quality metrics. You see, all metrics share a common goal, a goal we can exploit. That goal is to order videos by perceived quality. That's what a mathematician would call a total order. That is, we want to say that the video sequence A1 is worse than A2, and A3 is better than A2, therefore A3 is better than A1. Most also want to include with quality, which is why we talk about just noticeable differences. If two videos aren't noticeably different, they're equal in quality. Deciding something's better than something else is, well, a decision. Now, sometimes we phrase these as prediction problems. That is, predict on a scale of 0 to 100 what the perceived quality of the video is. But when it comes to encoding, it's a decision problem. Which of these two methods is better, or are they equal? You'll note, deciding on the order and quality of two videos is the basis of almost all subjective video metrics. And when performing statistical classification, we call the line or function or hypersurface that partitions things into two classes a decision boundary. Taking a mean of the underlying image scores to order the qualities of videos is just a very simple decider. A support vector machine or a neural network is a very complex decider capable of learning hyperplanes and nonlinear functions. The science of attacking these classifications is what we call adversarial examples. An adversarial example is an instance with small intentional feature perturbations that cause a machine learning model to make a false prediction. Generating a more spread out distribution was a simple adversarial example for the classification or function arithmetic mean. So how do we generate adversarial functions for generic functions? Well, our goal is to maximize the incorrect decisions of that previous decision boundary. Papernaut et al. Presented a paper in 2017 for doing exactly this to black box systems. Here's how we do it, adapted specifically to video quality metrics. Step one, you predict VQ for a bunch of videos. Now, we've already done that. Everybody who's ever run VMath on a video has generated some training data for me. Step two, we train a surrogate model. For example, a neural network that predicts from the same data to the same results. Now, with VMath, we could actually use the internals of VMath and not train a surrogate. But we don't need that same accuracy. We just need to approximate the decision boundary, the shape of that function that VMath is using to order video qualities. Step three, we create a new synthetic video which maximizes predicted variance using heuristics functions. Now, you might be asking yourself, how do we what heuristic do we use? How do we maximize distortion? We actually already know this pretty well, right? We can add known visual artifacts like blurring, bloom, ringing, banding, and just general noise. We could also add unnatural patterns, which are easy to compress, but very visually obvious. For example, moire patterns. We can also just intentionally break important parts of the video that are small and don't affect the overall score. I could blur out the faces in a scene. Step four, rinse and repeat, aka gradient descent, to generate a maximized perturbation. And step five, use the surrogate model to generate that final set of videos which are bad for the target model. In this case, that would be VMath or whatever metric you choose. Step six, write an encoder that uses those perturbations which produce maximal effect to optimize for metric score over perceived quality. Now, you don't actually want to do this. I mean, it would be fun, but very, very useless. That would be a great example, though, of how not to build an encoder. Now, have I spent the time to actually do this? The answer is no. I said this is a theoretical attack. But I'm pretty sure it would work. And why? Well, let's recall this graph from earlier, which I said showed you VMath is pretty good. See those lines in the upper right-hand corner that are basically just flat? That's where the VMath predicted a score for the video that was perfect, and human viewers actually only thought it was an 80 out of 100. Really, any point where VMath is greater than DMOS is a point where we could optimize for score over perceived video quality. And remember Goodhart's law? Any measure which becomes an objective ceases to be a good measure. You might see that sometimes we accidentally build encoders which do exactly that. They optimize score over perceived quality. Actually, we already do it intentionally I mean, that's why your encoder has tune SSIM and tune PSNR on them. Please never use those options. That is unless your model or your measure is a perfect predictor of outcome. That is, we might say, one-to-one and onto. After all, the purpose of a video encoder is to exploit the human visual system. Indeed, we're trying to throw away the maximum amount of information that fools the human visual system into thinking an image is flawless. In some ways, our encoders are exactly adversarial example generators for our visual cortex. Now, it's my firm belief everything I've told you doesn't make objective quality metrics useless, just that you need to be careful in how you use them. Your encoder relies on some form of objective quality to make literally every compression decision. Should I split this block? What QP should I use? Etc. are generally based on some sort of metric or heuristic. Whether that's something as simple as sum of absolute differences, this is a screenshot from the X264 source code, or as complicated as full RDO decisioning based on mean squared error and SSIM. So there are really two major takeaways here. One, always check the outputs of your algorithm with real people. Left to itself, we will optimize for our models, not our vision. And our models are almost necessarily incomplete. I looked this up, kind of blew my mind. The human visual cortex alone has around 2 trillion synapses. That's 2,000 times the number of weights of the largest machine learning models in existence today. And to the average human being, that doesn't count. That's just the visual cortex. To the average human being, the stubble on an actor's face because they haven't shaved for a few days, and yes, I'm very conscious of my beard right now, is more noticeable than the dirt on the driveway. But to PSNR and SSIM and almost every metric we have, they are the same thing. Whether you do this testing with a few golden eyes and some blind testing in a room, or you do that with ratings pulled from users and sophisticated subjective metrics like adaptive paired comparison, which Sebastian Van Loon, who's talking this year and talked last year, presented, is up to you. But it's a good practice to do to make sure you're not building the wrong encoder. And the second takeaway is we need better, quicker to compute objective video quality metrics. Using metrics which better approximate the human visual system is going to give better results. You can't really have humans watch all of the thousands of possible encodes of a given video, and you definitely can't have humans watch all possible mode decisions for a video. We have to use machines to do this. We don't really have an option. And I thought I'd throw this really interesting paper that just came out in there. This is a nice piece of work that uses state-of-the-art video quality metrics for decision at the coding block level. It solves some things like not all video quality metrics are additive, so if you try to use like VMath in a single decision, you may not make the right thing because it's not a straight sum, which is why we still use PSNR there a lot, or sum of absolute differences or whatever. Now, let's take a moment to look at tooling for using those metrics, because like I said, you should be using them. I would say it doesn't hurt to compute these metrics for almost every video you produce, and you can have humans look at the bad ones and the particularly and suspiciously good ones. First, for outputs, you want per frame charts. These simply show the score of an underlying metric at each frame. You'll also want it to be able to compare per frame charts on top of each other selectively so that you can see 2 encodes per frame right next to each other. These help us pick out problems like iframe popping, rate control underruns, etc. We're looking here for big jumps or dips on a single frame, or slow kind of peter down in a sequence, indicating that the quality is dropping frame over frame. Next, especially for AVR video, you'll want rate distortion charts. These plot a computed distortion, aka your objective video quality metric, or even a subjective one, versus a rate, e.g. the bit rate of the video. We usually interpolate these to give a curve along which we expect an encoder to operate. That's not always perfect, but we try our best. Having fancy Violin Graphs like mine is very useful as well, since metrics today don't have sophisticated temporal pooling mechanisms, as I mentioned earlier. Being able to select between a few of those, like harmonic and geometric mean, is also very important. When we take the difference between those curves, the value is called the BD rate, where BD stands for that, and I'm not going to try. The BD rate lets us compare what the expected bitrate difference will be between two encodes at the same visual quality. The BD SNR, which is the signal-to-noise ratio, really can be applied to any metric, as we've seen. Lets us compare what the expected quality difference will be at the same bitrate. You'll want to be able to generate nice graphs like this, which will help you calculate what an encoding is going to save you in storage and CDN costs, because that's ultimately what we're doing here, is driving down that distribution size for better user experience and lowering our cost of operations. Now, there's some major gotchas when computing reference-based metrics. The biggest is that you need to ensure you're actually comparing against the correct source frame. If you do any rate changes, for example, 25 to 30 FPS, any deinterlacing, any changes in color space, any changes in pixel format, that all needs to be accounted for and done correctly, because that's all done before the encoder even gets to it. Any filters, for example, denoise, which is used on live all the time, need to be applied as well. Now, some encoders can do that for you, but it's not that common. So that's why a very useful tool in your tool bag is going to be to generate lossless encodes using X264 and X265 to apply that same filter graph beforehand so you can do the comparison. You can apply those options using -QP0 for X264. That's not in the standard. It's just something X264 supports and FFplay on the other side. And then the preset lossless for X265, that is in the standard. The reason to use 265 instead of 264 for this is 265 supports pretty much arbitrary pixel formats. 264 is limited to YUV 422. So unless you're comparing in that domain, you can't use the faster encode. Next, if you're using FFmpeg's compare function, watch out for that frame sync logic. The FFmpeg compare filter is actually built on top of FFmpeg's frame syncer, and it will invent frames for you if it does not think they're aligned, which causes some really, really weird issues that we spent a lot of time figuring out how to get correct. To counter that, you're going to need this thing, which the only reference to this is one Stack Overflow question, which was us asking ourselves how to fix it, which forces PTS alignment. You'll see there's the set PTS equals start PTS whatever. That is not correct for this use case for a whole variety of reasons, but basically your encoder may jitter the PTS just a little bit, and that'll cause the frames not to sync. FFmpeg's PSNR also, by the way, is a very non-standard calculation. Do not expect it to match other tools. We can get into the depths of whether or not that's correct or not, but the way they do it is not the way it's usually done in MPEG and other tools. Now, to help with all of this, I would have loved to say this is online now, but it's not quite ready. Bitmoving is going to release our quality evaluation framework. The framework is designed to work with large numbers of long videos, where a single VMAF eval could take several days or weeks. I was getting to the point where I could encode AV1 faster than I could run the VMAF on it, and that was a problem for me. So this framework actually takes the video, segments it, calculates the correct frame alignment, and dispatches to AWS Lambda to perform the calculations of each segment along with appropriate frame offsets and alignments. That means it can by default run on up to about 2,000 cores, which is important because when you're doing a complex ABR comparison, you could have 5 encoding technologies, 10 clips, and 7 ABR tiers, and suddenly you have like 350 videos to compare. and those could be an hour in length. This framework also, all those pictures of the graphs, that's generated out of the JSON output of this framework. So should be a useful tool for the community. Thank you.